Okay, this is the lecture video for MAC 1140 Pre-Calculus. We're in section 10.2 where we are going to look at parabolas, which is a specific type of conic section. In this chapter, we're going to concentrate on three conic sections: parabolas, also ellipses, and hyperbolas. But in this section, we start off with just parabolas. So the definition of parabola is as follows. A parabola is the collection of all points P in a plane that are the same distance d from a fixed point F as they are from a fixed line D. And let me point that out, what they're talking about in that sentence. So these are all the points that make up the parabola. So what they're saying in this first sentence is that all of the points that are on this parabolic curve, they are defined in the following manner: that you should be able to get from any point on this curve, and we've chosen in this picture, this is the point that's been chosen, but you could actually do it from any point, to a fixed point called F, and this happens to be called the focus, which they mention in the next sentence. The distance that it takes to get from any point to the focus should always be equal to the distance that it takes to get from that same point out to a line, which they refer to as D and is otherwise known as the directrix. Okay, so if it is a collection of points that describes a parabola, this will always be true, that this distance to the fixed point will be equal to the distance to the directrix. Okay, and then they just go on to say the names of F and D, focus and directrix, which I've already mentioned. So we have a picture here. I would also like to point out things that you've seen before. The line that splits the parabola down the middle, it intersects the focus, the vertex, and hits the directrix at a 90-degree angle, is called the axis of symmetry. The axis of symmetry that you're seeing here that splits this parabola into two symmetrical halves is always perpendicular to the directrix. Notice that the axis of symmetry comes down right down the center of the parabola, but the directrix is on the outside of the parabola. It is always behind the vertex. It makes no contact with the parabola. It does not intersect the parabola. These are all things to think about because you're going to be focusing on this value called A. And that value is going to help us write the equation of the parabola. It's going to help us to graph it. It's going to help us to find a value called 2a, which will help us find points on either side of the parabola. These will be called the lattice points, and we're going to be very much concentrating on the value of a, the value of 2a, and how 2a allows us to get those lattice points so that we can graph the parabola. Okay, so I will demonstrate here, I'll just put it right into the diagram, that the distance A is this distance right here, from focus to vertex. That's called A. And it happens to be the same distance as the vertex is to the directrix. So this is also A. On the next page, I'll give you a picture of a parabola that shows the lattice points and the line that connects those two lattice points, but you're going to see that in that picture. From knowing these A values, it will be true that if you go from the focus to a specific point called a lattice point, that distance will be 2A. And I will demonstrate that in many of the problems as we go forward. Okay, this is just another picture here of a parabola, sideways parabola. You see that the vertex is right here at the origin. You know that's the origin because here's the y-axis, here's the x-axis, and where they intersect is the origin. So this is what we call a parent graph, whenever the vertex is right at the origin. The only difference between these two pictures is that this one's not superimposed on a XY grid or an XY system. So this one is, and you can see that the vertex is right there at the origin. That's what we refer to as a parent graph, or in other words, a graph that has not shifted to the right nor to the left, nor has it shifted up or down. So it's experiencing no translation whatsoever. Okay, I also wanted just to remind you of the basic distance formula, just in case that's required in this section for any of the problems. It's used a lot has been used a lot in your previous algebra classes, but just to allow you to recall that definition. The distance between any 2 points is the difference of the x values squared, difference of the y values squared. Those two squares would be added together, and you take the square root. Okay, all of this is what I verbally just explained and pointed out in the diagrams that you see here. Okay, moving on to the next page. I've included in your outline a picture of what's called the lattice rectum. And every time that we go to graph these parabolas, what's going to happen is you're going to be plotting the vertex. You're going to need to know where that graph starts. So right here, you're going to need the vertex. And sometimes that vertex is at the origin, but other times it will be shifted. It'll be shifted away from the origin. But in any event, you need the vertex. And you're also going to need to know how wide the parabola is right at the point, at the focal point. This focus can also be called the focal point. So it turns out that whenever you are going from the focal point out to the side, out to one side of the parabola, this would be called one of the lattice points. They just happen to call this one lattice prime, and this one is just lattice. These are lattice points. And the distance from here to here, whenever you're going from focus out to a point on the side of the parabola called the lattice point, that's a distance of 2a. And it doesn't matter which side, these will be directly across from each other. In fact, all three of these points, the two lattice points and the focus, they are all collinear. They all have to line up. And this is going to help you determine the width of the parabola. And we're going to be looking at that very much. The directrix, as I stated in the pictures on the previous page, that directrix is always on the outside of the parabola. It's behind the vertex. The axis of symmetry, also referred to as the transverse axis, that axis of symmetry will come right through the vertex, travel to the directrix, and hit it at 90 degrees perpendicularly. Okay, so you're going to be asked all kinds of things to name focal points, to name the lattice points, to give the value A, to give the value 2A, which will help you determine the other points I just mentioned. You'll also be asked to name the directrix. And any line, this happens to be a vertical line in this particular picture because sometimes the parabola opens sideways and sometimes the parabola opens vertically. This is a horizontal parabola because it opens sideways. So I'm going to give you the form of the equation for all four parabolas. It can either open upward, vertically, upward. It can open vertically downward. It can open horizontally to the right or horizontally to the left. And we'll go over all the equations. Just one of them is given in the theorem. But this directrix, when you are asked, it's either going to be a vertical line or a horizontal line, depending on what direction the parabola opens. So this will either be vertical or horizontal. When it's vertical, all vertical lines are named x is equal to, and then the value that it goes through on the x-axis. Okay, and the reason I'm calling that negative a is, remember from what I just said on the previous page, from vertex to directrix is always a distance of a. So if you're A units to the left of the origin, that would be designated negative A. So in the theorem, moving on, so we can get to the equations for each different direction that a parabola can possibly open in. This is just one of them. This happens to be a horizontal parabola that opens to the right. Okay, this is known because the A value is positive, and as I give you all four equations that indicate the direction that the parabola opens up in, you'll see that which direction it opens up in, up versus down, to the right versus left, is controlled by this A value, specifically the sign of the A value. Okay, what we have here just to start with in our examples are just a couple of questions that basically do what my math lab always does, elicit whether or not you understood the definitions and whatever theorems have been given at that point. So this is fill in the blank. A parabola is a collection of all points. That definition was given on the previous page, page 1. It's a collection of points such that the distance from each point on the parabola to a fixed point, which is actually called the focal point or the focus. This is just when they talk about each point, they're talking about any random point on the parabola, equals the distance to a fixed line, and that fixed line is called the directrix. All of that in the picture on the first page. The line through the focus and perpendicular to the directrix is called the axis of symmetry, which I pointed out to you on those first two pictures. So just getting some terminology out of you. Example 2, for the parabola, y squared equals 4ax, the line segment joining the 2 points a2a and a negative 2a, and you can see that picture right here. This is one lattice point, this is another lattice point. Its coordinates for one of the lattice points will be a2a, and the coordinates of this lattice point are called a negative 2a. And the line that joins these 2 points is called the lattice rectum. Okay, moving on to example 3. In example 3, we have all the different equations, or some of the equations that you can use, because remember, sometimes you can have a parabola where the vertex is right at the origin, right at the point where the y-axis crosses the x-axis, and that's what these 4 pictures are. These are graphs, parabolas that have not been shifted but have their vertex right at the origin. And in those cases, you're going to be using the equations that you see here. Note that when the parabola opens sideways, it's because the square is on the y. Notice both of these are like that. Yet when it opens up or down, the square is on the x. Notice that in all 4 of these equations, that you have one square term, but yet the other variable is linear. A is not a variable, it's a number. It stands for a number. Well, I guess you can think of it as a variable, but the only variables that we're specifically looking at is x and y. This is going to be a value that we're going to find. It's a distance. A is a distance. Maybe put that there so you don't confuse it with the actual variables x and y. But anyway, again, notice all of these have one squared variable and then one linear variable, one first degree variable. Same thing here, one squared, one linear, one squared, one linear, one squared, one linear. So they all have that in common. Notice that there is also something, the negative sign, that'll be involved in this coefficient of the linear term. This is the coefficient of the first degree term. When that coefficient, specifically when the a value is positive, on your sideways parabola, then the sideways parabola, the horizontal opening, will open towards the positive numbers. When the A value is negative, thus making this coefficient negative, then it will open to the left. It will open horizontally towards the left, opening towards the negative numbers. Okay, then you come to your vertical parabolas, which means it either opens up or down. You could say it that way as well. If the A value is positive, it will open upward. If the A value is negative, thus making this coefficient negative, the 4A coefficient, then it'll open downward. That's also going to be true if we take the vertex and we shift it away from the origin. And those are the equations that you are seeing right here. These are all shifted graphs where the vertex is no longer at the origin. They still take the same form that you're seeing here, where you have one squared variable and then the other variable is involved in an expression that is first degree. Same thing here. Same thing for this third one, same thing for this fourth one. One expression is squared, one expression is first degree. And again, that is going to tell you whether it's sideways. These are the two horizontally opening parabolas. Horizontal parabolas. Again, if it's squared and the coefficient is positive, it's going to open to the right. Just its vertex will no longer be at the origin. And if it's y squared, but that 4a coefficient is negative, it's going to open to the left. Likewise, just like what you saw up here, if x is squared, but the 4a coefficient is positive, it'll open up. And when it's x is squared, that expression, and the 4a coefficient is negative, it'll open down. The only difference here is that instead of the vertex being at the origin, 0, 0, it is now at h and k. And you're going to switch the sign as you pluck these numbers, h and k, from the equation to an actual point where you're listing the point and getting ready to graph. You have to switch those signs. Minus signs in front of any values that you're taking out of an equation always mean to switch the sign. Like this says x and then the opposite of h. That's what minus means there. So remember to switch their signs as you pull them out and list them so that you are getting ready to graph. Okay, in example 3, we start with, just the basic problem, and then we're going to get into one where you see all the values and you have to calculate them yourself. So you're given a picture here. What you're supposed to be noticing here is that this vertex is not at the origin. It has been shifted to the right and it has been shifted to the left, and you're trying to pick out which of these four formulas would be used if they had thrown some numbers at you. They did not. There's no numbers in here. So again, whenever the parabola opens either up or down, you're going to have your square on your x. The 4a coefficient is going to be positive here because it opens upward, and that's because the a value is positive. If a is positive, the 4a coefficient is positive. And you're giving the formula where the square is on the x, but the y variable is first degree. So that would be this one. So that would be the equation for a picture of this nature. Okay, moving on to example 4. Time to copy that. So in example 4, okay, so now we start to get some numbers. They're giving us values at the vertex. They're giving us an A value. Let's go ahead and put that A value so you start to get a sense of what does the distance A stand for. It is defined as the distance from the vertex. Oops, I'm putting it in the wrong place. From the vertex to the focus. So A would be equal to 4 right here, from vertex to focus. You could also define it as the distance from the vertex to the directrix, which really doesn't concern us in this problem, only because of the question that they happen to be asking. They want to know, what are the coordinates of the focus? So we're going to give coordinates here. We're going to give an x and a y coordinate. Well, if the vertex right here is at 3, 2, and you're moving up from the vertex to get to the focus, that means your y coordinate is changing. Whenever you move either up or down, it's only your y coordinate. You're staying aligned with this vertex, which means the x will stay the same, but yet your y value will go up, and this is how much it's going up. So when you go to list this point, keep the x the same while changing the y by a distance of 4. So this would be 3, 6. And example 5. Find the equation of the parabola. Find the 2 points that define the lattice rectum. So we're going to have to find the lattice points, and we're going to use those lattice points to graph the equation and give the exact width on that graph. Okay, so very much concentrating on finding lattice points and the A value that gets you the coordinates of the lattice point. So it says the focus is at -7, 0, and vertex is at 0, 0. And you very much want to get into plotting whatever points they do happen to give you, just so you can get a sense of which way this thing opens up. Because based on the direction that the graph opens in, that's how you're going to be able to tell which equation to use. And they're going to be asking this in a lot of problems. So if I have a vertex at 0, 0, this is my vertex right here, and I have a focus at -7, 0, that would be that one right there. And then you have to remember the parabola opens always from the vertex, so maybe you want to label these. And it always wraps around the focus. And all the pictures that I've shown you on page 1 and 2, the focus is always inside the parabola. So what you're going to have here is this vertex opening up around that focus. And just by visualizing that your parabola opens this way, wrapping around the focus, you now know that it is one of these kind of parabolas. It is a sideways parabola, which means the square is on the y expression, and it opens to the left. And when it opens to the left, that means that the A value is negative, and therefore that 4A that plays the role of the coefficient on the linear term, it's also going to be negative. So the form of the equation is this. For anything that opens sideways into the left and has a negative A value. Okay, now I notice that this vertex right here, and you should notice also that the vertex is right at the origin, which means this is not a shifted graph, so don't use the shifted equations, use the unshifted equation. So this is going to be y squared, that makes it open sideways. The 4A value, since A is going to be negative, and that's because it opens to the left. That's how you know that the A value is negative. So this entire coefficient involving the A value would also have to be negative, and then you would have times your linear term. One squared term, one linear term. The 4A value plays the role of the coefficient of the first degree term, the linear term. So that would be your equation here. Now, as far as a vertex and a focus of -7, 0, let me fill that right in there. We need an A value here, though. So I'm going to write here that I used this equation, and then I want you to see me plugging in the A value, thinking about how to get that A value. So remember that I was showing you on the previous pictures that when you're going from the vertex to the focus, that is defined as A. Well, if this is at 0, 0, and this one's at negative 7, 0, and you want to think about A in its positive form as a distance, this would have to be 7. The negativity is going to come from the formula. You want to think about your A value as a distance. When we wrap an absolute value symbol around anything, that means think of it as a distance. Because absolute value does mean distance. So this would be 7. So now you come over here, and all you do is you take that and plug it in for A. So it'd be negative 4 times your A value times X. And in the end, you get the exact equation using the numbers that were thrown at you for vertex and focus, and using those to help you figure out the A value, which was 7. So now this becomes negative 28x. And that's the final answer you're going to give. So this is just the formula. You have to find A. That turns it into this. Y squared is equal to negative 28x. Okay, so we had that answer there, that answer there. Okay, moving on to example 6. Give me 1 second. Okay, so example 6. All right, find the equation of the parabola. Describe, find the 2 points that define the lattice rectum, and graph the equation. I want to make sure that I gave all answers for example 5. I think I gave everything they asked for. Let me just check that real quick. Oh, no, I didn't. I thought I left something off. Okay, so the 2 points that define the lattice rectum. Let's just continue with this one before we go on. Okay, the 2 points that define the lattice rectum. Okay, so those 2 points are lined up with the focus. These points line up with the focus. In fact, they're on either side of the focus. Again, let's refocus here. The vertex, right from the vertex, the parabola opens up around it. Now we want to know how wide does this leg swing, how wide does this leg swing. So that means the lattice, we need those lattice points. So if the A value is 7, then 2A, again, think of it as a distance, would have to be 14. So that means if we're going to line up with the focus and go wide this way and wide that way to figure out how wide the actual parabola is, we're going to have to go 14 spaces, because always from the vertex out to the side of the parabola, whether you're going this way or this way, to get those lattice points is a value of 2A. So we're going to go from where we are right now, 14 spaces. So we're going to be, let's see, that's right there. Right there. We're going to go all the way up to, that's 13. This would be 14 right here, because that's 15, that's 16. So this is going to be one of your lattice points. They like to call them, I'll just call one of them lattice point. But those lattice points are -7 and then your 14 units up in the air. You can just put them here. -7, 14, and if they just give you one blank space like this, then they just want you to separate them by commas. And then the other one would be 14 down, so you would be at -7, but you would come all the way right here. So that's -13, -14, so this would be the other lattice point. -7, -14. Okay, as soon as you get those two lattice points, you now know the exact width of the parabola. So right from your vertex, you will just come right through both lattice points in order to complete your graph. And you know when you go in My Math Lab, they're going to ask you to pick the shape. It'll be a parabola. And then you'll feed in the vertex and the two lattice points to define the width of the parabola. So this was -17, -14. So we gave the equation here. We gave each of the lattice points. The vertex was given to us, but by using the vertex as well as the lattice points, we're able to get the graph. So this is pretty much what you're going to be doing in many of the problems. What's going to change from problem to problem is what they present you with at the beginning, but all of it will be enough information in order for you to get the A value so that you can then get the 2A value and graph your graph. Okay, so in example 6, it says find the equation of the parabola described, find 2 points that define the lattice rectum, and graph the equation. Okay, so in this particular problem we have, this time, we're given the directrix. That is the line that is behind the vertex. It does not cut through the parabola at all. They want the equation of the parabola. Let's go ahead and start drawing these things so we can get a sense of what is the A value, because we're not going to be able to write the equation without the A value. And we're not going to know what form of equation to use unless we can see what direction it opens up in. So that's why we start off by graphing what little information we do have. Right now we have the vertex. Well, you might want to label that so that you can get a visual on this. We have a directrix. A directrix is a line. You have to know how to draw your lines. When it's x is equal to, well, I'll just remind you here, x equal to any number, the line looks like this. Because if they're going to start off by giving you information about lines, which represent the directrix, you need to know which way to go with them. If it's y is equal to a number, then the line runs like this. Okay, so let's see, right? Just with these two pieces of information, it's going to tell us which way, which direction the parabola opens in. So let's go down to y is equal to -1.5, because 3 divided by 2 is 1.5. So we're going to go right here. Let's see, this is -2. Let me slide this up. This is y is equal to -2. So this would be 1.5 would be right here. Let's see, that would be 1. -1, this would be -1.5. So right there is y is equal to -1.5. Or you can write it just like they gave it to you. And I'm going to extend it this way. Okay. So then let's see. If I am going to open from the vertex, and I'm going to avoid intersecting with this line called the directrix. Remember, the directrix is behind the vertex. It never makes contact. That would mean the only possible way I can open, I know that I have to open right from the vertex. If I open up, I will completely miss this directrix, making no point of contact with it, which is the way the directrix is always situated. If I open down, I'm going to intersect this, so it can't be down. If I open sideways, I'm going to intersect it. If I open sideways left, so the only possible way that you can open is up. Furthermore, you should understand that what they're giving you here, although this information is different than what you were given in example 5, it still gives you a way to find the A value, which thus gives you a way to find the 2A value. Because from vertex to directrix, that is also the A value. You can either go from vertex to focus, which we'll put that in there, if we need to, or you can go from vertex to directrix. Both of those are the A value. So you're going from here to here, which is a distance of 3/2. Remember, we're always thinking about A. I don't want you to think of it as negative 3/2. I want you to just think of it this way. You can write it as 1.5 if that's going to make it easier for you. Okay, you can turn it into decimal just as long as it's not a run-on decimal that you're going to have to round off because we want exact answers here. Okay, so now it says, what is the equation of the parabola? We needed the A value, and we have that A value. We also know that this parabola is going to have to open upward, but I want to wait before I graph it completely, and that requires the two lattice points, which I need the A value for. Because if this is A, then 2A would have to be 2 times 1.5, which is 3. Okay, so I'm going to plot my focus as well. The distance from vertex to directrix is A, which was 1.5. It is also the distance from vertex to focus. I need that focus in place because from the focus, I'm going to move sideways 3 units to the right, to the left in order to get the sides of the parabola. So if I went 1.5, 1.5 this way, I have to go 1.5 this way. So this would be 1 this way. This is where your focus is. Remember, the focus, the vertex, and the point down here were 1 point on the directrix. Those all line up. And this is also a distance of A. I can't put too many numbers in there because it'll get all scrunched together. So now if I wanted to get the actual sides, how wide they are as I open this way, we've discussed that I'm going to open up. I need to move a distance of 3, and that's from the focus. The focal point lines up with the lattice points. So let me just get this out of the way. Put it right here. So if I wanted to go out this way, 1, all the way out to 3, that would be right here. So right here, but line up with the focus. Okay, so that's one of your lattice points. I could just call it L prime. And then if I want to go the other way, but go to 3 going the other way, that would be right here. This would be -3. And I could get right up there to where the focal point is. And have the other lattice point. Now they're going to ask you for coordinates for these. And you can graph it first if you want to, or afterwards. Okay, so there's our nice graph, perfect width on that thing. You need exact width or my math lab's going to mark it wrong. And if you're being asked, you know, what the coordinates of those 2 points are, the 2 points that join, that create this lattice rectum. The line itself is called the lattice rectum, but if you're referring to the points, we just call it as the right and the left lattice point. So this one is located, as you can see, at 3, and it is 1.5 units up in the air, right there. We went 1.5 units up that way. So that's one of our points. 3, and you can either call it 1.5 or you can call it 3/2. And then the other point that's over here is just that -3, and it's 1.5 units up in the air. And they won't, my math lab will not dictate, I don't believe, which one you list first. You can list either of them first, but if they give you one blank spot like this, you just separate them by commas. When it says what is the equation, well, just finding the A value was enough. What you need the 2A value for is so that you can name the lattice points and use the lattice points in conjunction with the vertex. In other words, just connect them all in order to get the graph. So the equation, when it opens up, is like this. This is the formula. And let's see, this vertex is at the origin, so we are not using the shifted formulas. It would just be x squared. Since it opens up rather than down, it will be positive for a coefficient. That's because our A value is positive, which we know from the way it opens up, times our linear term. We did know the A value, so we can give a more exact answer here. We could go like this, that x squared was 4 times the A value, which was 1.5, or you can write it as 3/2, times the linear term. So this would be 12. 4 times 3 is 12, divided by 2 is 6. So it's x squared. After you multiply this times this, instead of having 4a, you now have 6. Okay, and that is the equation for example number 6. Okay, these are the lattice points. Those lattice points in conjunction with the vertex help me get the graph. And that completes problem number 6. In the next video, I'm going to be doing numbers 7 through 11.